Welcome everybody to the next installment of our weekly reading group. Today, really excited to welcome Zilong Wang. He's a fourth-year PhD student at UC San Diego, advised by Professor Jingbo Shang. He spent time doing research at Google Cloud AI, Google Research, Adobe Research, and Microsoft Research Asia. He received his bachelor's in computer science from Peking University in 2020, where he was advised by Professor Zilong Wang. Today, he's going to be presenting his paper, Speculative RAG, Enhancing Retrieval Augmented Generation Through Drafting. So really excited to go through this today. And yeah, the floor is yours, Zilong.
Thanks everyone for being here. It's a great pleasure to introduce my recent work, Speculative RAG, Enhancing Retrieval Augmented Generation Through Drafting. This is a collaboration between me from UC San Diego and Google Cloud AI Research Group and the Google DeepMind. It's my work from my past internship. I spent a wonderful time there. And here is the paper link. Feel free to click it to check the archive version. Let me begin my presentation. So first thing first, let me briefly introduce the RAG, the Retrieval Augmented Generation. I believe most of you should be familiar with this, but let me just repeat it again. So when we use large language models, we just use it like a chatbot or some search engines, perhaps. However, we can see currently large models still struggle with spectral errors and hallucination contents when they are solving like very knowledge-intensive questions. So basically, we know large models are trained on large corpus, but maybe sometimes due to the capacity or some other mysterious reasons, large model cannot do it well. So here, I don't know whether the RAG is the ultimate solution or a temporary one, but we can see RAG indeed did a great job here. Basically, in RAG, it will incorporate information retrieved from external knowledge base into the context of large model, so that large model will have more up-to-date information and more specific facts to answer your question. So as illustrated in this figure, I copied from some Google Docs. You can see with this RAG, the model will have more grounding truth and the knowledge will be up to date, and it's like a more comprehensive search engines for you. So basically RAG can solve this problem well, but I'm not sure it's the ultimate goal, but let's see. So this is a very popular topic. There's a lot of recent efforts on RAG. First thing first, since we need to incorporate the retrieved document into the context, so one direction is to extend the context length of our models. If you go back and see the large model since the ChatGPT came out, there's the content window is larger and larger. I still remember when I used BERT, the context window length is only 512, but you can see how long the context window is for now for current large models. Another thing about the retrieval side, you can refine the retrieved document with some tricks. Maybe you can use a large model to summarize it, to maybe rewrite it, to do many different refinements on the retrieved document, so that the model, when it answers the questions, it will have better documents, better contextual information. However, in this work, we are not exploring in these two directions. We are actually trying to strike a balance between the efficiency and effectiveness in RAG, so that we can incorporate more documents into the context without sacrificing the latency. Because we all know if we have more documents, the inference time and maybe the quality of the inference will both be influenced. Those cases is not that ideal. So this is some like high-level idea of the speculative RAG system. We offload the computational burden to a smaller specialized language model. It serves as an efficient and robust RAG for existing general large language models. On the left, that's the kind of the standard RAG. That's a kind of a usual paradigm when we do the RAG. The large language model could be a Gemini, could be a GPT-4, could be Llama 3. That's very, very large. So if we input too many documents to it, there will be long latency, and maybe the complex reasoning will lead to hallucination. On the right, that's a speculative RAG. As I mentioned, we are not input the document to the original very large language model. We are not inputting the document to a Mixtral 8x7B. We input it to a smaller one, Mistral 7B. For the Mistral 7B, which is smaller one, we call it the specialist RAG module. This is the red box here. This model is fine-tuned for the RAG, specifically for RAG. It's smaller, and we believe since we fine-tune it, we expect it have the capability of RAG. That's it. We don't expect it to do many fancy different general things just for the RAG. So in this dissolution, actually we are doing dissolution on this small language model. So yeah, but we all know that smaller model is not strong enough. So we just do some trade-off. We generate multiple drafts with this small model, and we use the original large ones to verify it. So we still leverage the original general capability of the larger language models. So finally, the larger language model is like a ranker. We rank the drafts and select the best one as the final answer. So you can see we kind of reduce the latency through several steps. We use a smaller model, and although we generate multiple drafts, and this generation can be done in parallel. So basically, that's the two strategies to reduce the latency. And for the effectiveness side, we also did some more improvement to guarantee the effectiveness is still there. And I will just go through it in details later. Yeah, and as you may tell from the name, the idea of speculative RAG came from the speculative decoding. I'm not sure if you kind of familiar with this, and it's like another big topic in large language model study. So basically, in the speculative decoding, there are also one small model, one original large model. But the biggest difference between our idea and speculative decoding that in speculative decoding, they predict the future tokens. Well, in our case, we predict the drafts. So in speculative decoding, it will generate a few more tokens with the smaller model. We know smaller model is fast, but of lower quality. So we use the original large model, which we want to accelerate to verify these future tokens, to accept a few and abandon a few if you are not lucky. So if you accept a few tokens, then okay, good luck. The original large model can be accelerated in this way. So basically, we just borrow this speculative idea, this drafting ideas into the RAG system and try to generate more drafts and verify it to balance the latency and accuracy. Okay, this is the main figure of our model. In this row, you can expect it as the original large model. When it meets with a knowledge-intensive query, which needs some external knowledge, we will hand over this job to the smaller model. With smaller model, we input it with the question for sure, and a subset of the documents. So here, the 1 to 6 are 6 documents retrieved from the database, and we just split it into several subsets. And we input each drafter with a question and the documents and generate the alpha. Alpha is the answer draft. Beta is the corresponding rationale. So yeah, the specialist drafter will generate two things. One is the draft, the other is the rationale. And we will use the original large model to rank this alpha 1, 2, 3 based on the beta 1, 2, 3. We will rank the draft based on the rationale to select the best one. There are 3 stages. You can see the blue ones are using the original large model, and the red ones is using the smaller drafter. This is some pseudocode.
Very quick question there, sorry.
Sure.
The question is the question exactly the same then? So the question you ask the generalist LM, you pass on exactly the same unmodified question to each of the specialist RAG drafters, basically.
Yeah.
So when generalist encounters knowledge temperature queries, but when you say it goes to the generalist first, what does the generalist do at the beginning then? Like, why does it not just go immediately to the specialists, and then the generalist assesses them? What does the generalist do at the very beginning?
Actually, it's the same. This figure is to like simulate a realistic scenario. You can consider Google is running Gemini all the time.
Oh, sure. Okay.
OpenAI is running the GPT-4 all the time. And okay, now
okay,
there's a user query come here. Okay, let's use
But actually, in terms of the data flow, in this case, the generalist doesn't actually do any processing before the specialists, really.
No.
Okay,
the specialist is just there waiting for the knowledge.
And the number of specialists is a hyperparameter that you set basically at the moment.
Yeah.
I wasn't sure if like the generalist decided how many specialists to use or anything like this, but it doesn't.
Yeah, that's a great idea. Yeah, basically that's something we can do. Yeah.
Okay.
And actually, for now, the number of specialists is decided by my GPU's resources. I just need to, it's always short of GPUs.
Makes sense. It's also interesting the extent to which this is just kind of a random search across the pairings of the documents, because I guess a big part of this is partly the random seed and the temperature and just like the natural variation of the specialist. But the bigger vector of randomness, presumably, is the documents that are selected. Like you have these vector embeddings and you pair the documents together in a somewhat random way. And I guess that's the most important search space that you're searching across with these many specialists, I guess, right?
Yeah. How to select this kind of subsets is a very important problem. We try several strategies. We can go through it later.
Sure.
And I have more detailed numbers in the paper. You can check some addition studies in that.
Yeah, sounds good. Okay, makes sense. Thanks.
Yeah. Okay, this is pseudocode. I guess you guys don't have the patience to read it through, so let's skip it. It's also in the paper. Yeah. So as we discussed, there's 2 major components in this RAG system. One is the drafter, the other is the other is a generalist. So for this drafter, because it's small, we cannot expect it to be very powerful, even we generate multiple drafts. So here we still use some distillations. We are using instruction tuning to make sure the smaller model can be better at RAG than it originally. So we distill the RAG reasoning capability from a larger language model to this speculative language model. Sorry, my cat threw away my AirPod box. Sorry for that. And so in this instruction tuning, we are just tuning this smaller language model with the normal next token generation. The training set composed of 4 parts. The first one is the question, the second one is the answer, the third one is the retrieve document, and the last one is the rationale of the answer. Here is how we get this training data. For the question and the answer, we just get it from many open source instruction tuning data sets like OpenInstruct and many other data sets. For the retrieve document, we are using the retriever to retrieve the document with the question from some database, from knowledge base. For the rationale, it's part of the training. We synthesis it by using large language models. So equipped with these 4 components, we can distill the RAG capability to this smaller model.
Sorry, just to fully understand, are you're
Sure.
just training the summarizing step? You're not training the embedding model?
Oh, no, this is not the embedding model.
Okay, and the embedding model is just fixed, basically, in this paper?
Actually, we are kind of involving 2 embedding models in the system. I'm not sure which one you are talking about. Are you talking about the retriever side, or?
Yeah, I'm talking about the embedding model for the documents, basically.
For retrieving the documents?
Yeah, exactly. Yeah.
Oh, I see. No, we are not training that. Actually, in our experiment, we are using the same retrieved document. So basically, in the data set, the documents are already retrieved there. I can tell you the retriever they are using, but I don't know. I didn't use the retriever myself.
And the kind of thing you're trying to get these smaller models to get better at is like avoiding hallucinations and making sure to like use the information that's given in the context window correctly, and just to kind of be better at doing that, basically.
Yeah. So supposing if the larger one, the biggest large models capabilities there, and the smaller ones here, we just want to train it a bit, to raise it a bit.
Yeah.
But we didn't expect it to reach the
and what are some of the kind of errors that the smaller models would have? Is it kind of just not listening to the information in the context well enough, or kind of making things up even when it's in the context? Because in a way, like the summarization step is often, I don't know, like on some tasks it's quite easy, on other ones it's very hard. Do you know the kind of things that it would normally fail at typically?
In this training, we expect the smaller disruptor to have the capability to reason based on the document each is given. So what we want to avoid is it just generates some answer on its own, ignoring the document. That's the bad case. We are trying to
so you just want it to be like really like very, very clear. This is the context. You need to answer your question based on this context.
Exactly.
Make sure I always do that really well.
Yeah, even if the context is wrong.
Yeah. Makes sense. Even if it knows with its own latent knowledge about the world that the context is wrong, it still needs to like use the context, basically.
Yeah, so that's why we call it a specialist. We cannot expect it to do other general things.
Yeah. Makes sense.
Yeah, you can. And another thing that about this tuning is that you can pay a bit attention to the log targets. So what we want to generate with this drafter is both the answer, the A here, and the E, the explanation, or call it rationale. So we want to generate these 2 things, and we will use these 2 things to verify and evaluate the answer drafts. And okay, comes the drafting stage. That's also the key step, just like what Daniel just noticed. Yeah, here I draw some figures, then it's easier to understand. Yeah, the first step, we will cluster the retrieved document into several groups. Here, we expect each group represents a topic in the retrieved document. So basically, you given a question, right? You can search the document, search the web, search the Google or whatever database you have. Sometimes because of ambiguity, or maybe just the retriever is not good enough, you will retrieve several documents. Some of them are about something. Maybe, for example, you are searching for a people's name. You can Google my name There's a lot of other Zilong in Google sharing the same first name, even the last name. So in this case, if you are just searching for one Zilong, that's me, then there will be other irrelevant people, the information with the same name. So it is not expected. What we want is to group them. Okay, so in this case, maybe the yellow group is about 1 person, the red is 1 person, green is another person. Maybe this is searching for people. Maybe you're searching for other queries. It's also similar. It's just different topics, different perspective in your retrieved document. we are using this this embedding. This is some off-the-shelf embedder system. Embedding model. You can embed the document with regard to your query. So basically, you can just use this. This embedder is just designed for this task. It's very suitable here. So this document is clustered into these 3 groups with regard to the question. And here we are using k-means because k-means is very popular, very simple and useful. And we are not exploring maybe other alternative to k-means, but we just use it. After that, we have these 3 topic groups, and we select one document from each cluster into the subsets. So you can see we select 1 from the first group, 2 from document 2 from second group, and document 4 from third group into each subset. And as you can tell from the clutter, each subset will combine with the information from each topic. So each subset should have the diverse information from the retrieved document. For example, the document 1, each subset will contain different, 1 document for each different Zilong, and in the case I just mentioned. Yeah, so we will generate the draft alpha and the rationale beta with each of the subset. You can see in this example, the context for each drafter will be much smaller than the original one. Remember, originally we retrieved 5 documents, but now we just input 3 of them into 1 drafter. And the drafter is smaller, the generation can be done in parallel, so a lot of different things can improve the latency. And as you can see here, each context may have the diverse topics in the retrieved results. So basically here we are also covering the diverse perspective in the retrieved results. So we expect this is a way to guarantee the effectiveness. The last step is quite simple. We use the original larger language models to calculate several scores for each draft and rationale, and got a score to rank the draft and select the best one for the final answer. Let me go through these different scores in details. The first score, we call it self-consistency score. It is computed in this way. We give in the question and calculate the probability of the question and rationale. So we are leveraging the language modeling ability of large language models. So we expect a self-consistent answer and the rationale pair should have higher probabilities here. The second score here is called self-reflection score. In the conditional part, we have 4 things: the question, the answer, the draft, the question, the draft, the rationale, and 1 R. R is a self-reflection statement. We use this simple one here. Do you think the rationale supports the answer? Yes or no? It's like a prompt to let the large model, to ask the language model whether it thinks this pair, this question answer rationale pair is good enough. It's good or not. So here is another score here. And the third one is quite simple. That's from the drafter model. We generate this answer and score with the drafter. We'll have the probability. Yeah, we also consider that. We combine these 3 scores together and produce the final score for the draft, the row J, and select the best score, best draft based on this score. Okay, let's dive into the final result. This is our big table in the paper. We compare with these baselines on these 4 benchmark: Trivia QA, Music, Pop Health, and Art Challenge. For the Trivia QA and Music, they are 2 free-form generation question answering data set. The answer could be a short phrase or a short sentence. but the answer would be in a short form is just one unique answer inside of it. And for the closed set, you can think it as a multiple choice. For the pop-out, that's true or false. For the ARC challenge, that's ABCD. You need to choose one of it as your final answer. We compare two categories of RAG system. The first one is called standard RAG. That's a very common practice for RAG system. You input the document to it and get your final answer. For the second category, we also reproduce the result of these two more recent work. One is called self-reflective RAG from UW, and another one is corrective RAG. Corrective RAG actually is a very close following up work for self-RAG. So you can see they even have a self-C-RAG version. But anyway, here is the overview of the results. And in our experiment, we are using the Mistral. For the speculative RAG, the drafter is a fine-tuned Mistral 7B. And for the verifier, for the one to do the ranking, we are using the frozen Mistral 7B and Mixtral 8x7B. There are two versions. You can tell it from the tag here. It should be noted here for the verifier, we are not doing any training. We just use the original model. And you can see here, we are not using the instruction tuned version. We are using the original version. We just leverage the language modeling capability of these large language models. So you can compare these two rows. For this verifier, that's the Mixtral 8x7B without instruction tuned. We only tune the drafter, which is much smaller than 7B, and the training data is not large. It's not very large. You can check the paper. I remember it's 40,000 samples. It's not that large training. And you can see our performance is still quite better than the instruction tuned version. Another highlight here is the C-RAG, self-RAG compared with the this version. We use a smaller verifier, and basically in this comparison, we are using the same fine-tuned parameters. So basically, in self-RAG and corrective RAG, they are using 7B version. They kind of fine-tune the 7B parameters. However, in our case, also fine-tune the 7B parameters in the drafter. So you can see speculative RAG is also very effective. Very effective in the smaller models paradigm. Yeah. Finally, that's about the latency performance. For the latency part, we compare speculative RAG with the standard RAG. We use you can tell it from the legend. For speculative RAG, we are using the Mixtral 8x7B with a RAG drafter of 7B. And for the standard RAG, we use the best performing backbone Mixtral instruction 8x7B. You can tell it from the table. The Mixtral is the best baseline, and we are comparing this row with this row in terms of the latency. Yeah.
Quick question. Sorry, what does TP mean here?
Oh yeah, it's a tensor parallel.
Okay.
Yeah, the reason why I introduced this parameter here is that I couldn't run the Mixtral on one GPU. So I have to split it into several GPUs to make it runnable. So here TP equals 4 means I'm using 4 GPUs to do tensor parallel when running the standard RAG. I'm using the VLM package, so it's just like a hyperplanar here. Yeah. It will leverage multi-GPU to split the weights.
Okay, yeah. And how many how many specialist LLMs are you using in these results typically?
For TQA, I'm using five specialists. For music, I remember I Yeah, actually, I always use 5 specialists.
Was it
So you
5
can
on all of the previous graphs as well?
no, in previous or there's no dropper ID yet.
But
Oh, you mean this
the number
result?
of yeah on the speculative RAG, how many special was it 5 on all of these bottom results as
Yeah,
well?
5 for all of
Okay.
these.
Interesting, because 5 seems quite low actually. Depends how many documents you need to reason about, and how many documents was each specialist retrieving? Is that dataset specific or?
Yeah. For the TQA, Pop House, and ARC challenge, the total number of true documents is 10.
So 10 documents per specialist?
No, 10 documents in total.
Oh, okay. And how many documents was each specialist
2
indexing?
documents.
2.
Yeah.
Okay. So you have so in total you have the ability to look at all 10, but typically, and how, I guess the question is then, how do you, sorry, I know you might have explained this already, but how do you assign the documents to the 5 specialists then? Because I guess you have your question, you have the latent vector of your question, you then have the similarity search to the document embeddings, and then you get like you get them ordered, let's say, what's the ordering of how similar they are to the question. So how do you do this process? Sorry, how do you randomly group them?
Yeah, so
Okay.
it's also kind of relevant to our experiment setting because we are comparing with self-reg and many other baselines. We have to use the same retrieve documents with the same retriever, right?
Yeah.
So we just borrow their retrieve documents. They publicize their documents they are using. There are 10 documents here. We use this embedder. I have the link here to cluster this document into several topics and select one document from one cluster into
Got it.
a subset.
And
But here there's some
is the number of clusters fixed?
Yeah.
So yeah, K means cluster. So how many clusters does the number of clusters, sorry, I'm going quite deep. Does the number of clusters change depending on the data set?
It's also a hyperparameter. I didn't tweak it so much, so I set it as 5.
Okay, but so generally speaking, just to get a bit of an idea of the magnitude, you basically have 5 specialists in each case, and each case they take 2 documents, and those documents are sampled from K clusters that are clustered using the embedding model for the dataset, basically.
Yeah, just a bit details here. Because we are always using cluster, it's just a bit misleading, I have to say. We are not inputting the cluster of documents to the specialist, to the drafter.
No, sure. You're sampling from the clusters.
Yeah. We're sampling from each cluster.
Exactly.
You can see this gray box is what we is like the
so you want to make sure that each specialist has like a broad sample of the documents, because then it samples from each of the clusters basically. But what doesn't make sense? So, but given in this case you said before that there's like 5 models and they each have 2, that would mean that you only have 2 clusters. Like, do you link the number of clusters to the hyperparameter for the number of samples? Because that would like basically it seems like the number of clusters needs to be the same as the number of documents each specialist gets. Are they the same number?
Yes. That there are only 2 hyperparameter. One is the number of documents in each subset, and the number of the drafters. So you can simply compute the number of cluster based on those 2 parameters.
Okay, got it. Makes sense. Sorry, I just wanted to understand the details there a bit, but yeah, makes sense.
Yeah. So yeah, that's about the end of the slides. Yeah, you can see this is a great latency comparison. Our method can improve the latency as well. The unit of this is the second. Yeah. So yeah, and basically we can see that improving the tensor parallel may not improve the latency here. So you can tell from the trend is actually going slower and slower. So I don't like the tensor parallel either, but I have to use it to accommodate the larger model to the GPU I'm using. Yeah, that's all for the presentation.
Amazing. Well,
a few technical with here. No worries. Yeah, it's about the end, and any questions are welcome.
Amazing. Well, first of all, let's give a big round of applause to Zilong. That was amazing talk. I certainly have a ton of questions, but what I can say is, if anyone in the audience has any questions, then feel free to just raise the hand by pressing the hand button, and we can go through some questions. So I see that Mohammed has a question. Do you want to go first? Unless that was an attempted applause. No.
Yes, sure. I can go.
Sure.
I'll let the sir. He was before me. Atul. He raised his hand before. If he wants to go first.
Might have been a mistaken applause. Did you have a question, Atul?
No, I had my real hand up as opposed to my virtual hand.
Oh.
Go on, Mohammed.
All right, sounds good. I had a few.
Oh, we have an internet problem. It seems like. Maybe Atul, do you want to go while Mohammed's internet's hopefully getting better?
I didn't have a question. I was just
you're muted, Atul.
But,
maybe you didn't have a question.
Yeah, sorry.
Oh, okay. No worries. Well, Kato has a question. Kato, do you want to go? And then if Mohammed comes back, we can bring him in.
Yes. I wanted to ask about the scalability of these two different LLMs that they're using. For example, if you're working in the health sector and you're working with a lot of data sets and you have to break them down into chunks, how are they going to address that, the issue of having large data sets?
Let me see. I believe on the data set side, it's about like the very beginning of this this RAG system. We need to retrieve the document from the large data set you just mentioned and feed this document to whatever RAG system. Maybe our RAG system is one of them. For the retriever side, honestly, I'm not an expert on that, but my understanding is that first thing first, we are using the dense retriever. Basically, we will give each document a vector and give your question a vector. You can do some dot production to have a score for the relevance or maybe whatever things. And for these vectors, I believe there's also other techniques to store it efficiently. Maybe some sparse vector, I suspect, but as I say, I'm not an expert. I just read it from other papers. Yeah.
How about the data privacy of the data that you're sharing between those two LLMs that you broke down?
Yeah, for the privacy side, this is work I did at Google. So I expect both the general large model and the drafter language model are both hosted by one provider, maybe OpenAI, maybe Gemini, maybe whatever companies. So this drafter like extension for your original larger language model. So maybe the large model is hard to fix all the requests. It's hard to call RAG efficiently. So the provider does design another module specialized for RAG. So I expect that maybe the privacy side should be the same as the original large language model. Thank you.
Any other questions from anyone at all? I can quickly jump in with one if not. Sorry, of course, yeah. Sorry, Mohammed, your internet died last time. Go ahead.
Yeah, of course. Sorry about later. I have troubles with the connection.
No worries.
Call Seoul City, that's all. Okay. Thank you very much for this webinar. I've been trying to join since the 3 last meetings, but unfortunately, this is the first one I had the chance to join. Thank you, Zilong, for the presentation. It was very insightful. I have a question about how do you divide the different LLMs models used throughout your different databases? Do you choose each LLM for a specific database, or do you just divide them throughout all the database chunked, or how do you go through that process?
Yeah, that's a great question. For this work, we are not targeting for specific domain. We expect our system is for like a general domain. That's why when we train the model, 1 second. Yeah, when we train the drafter here, we are just collecting our training data from the instruction tuning data set for the general domain. We are not targeting for like the health domain for the pop health or other data set for some specific domain. We are designing it for the general domain. But for sure, if you are targeting for a specific domain, you can train your drafter with this specific domain knowledge. I expect it will do better for a specific domain if you train it with the relevant data.
Makes sense.
All right, understood. Thank you.
Any follow-on questions there at all, Mohammed? Or
Yes, sure. I've worked on RAG for my thesis in engineering, and I work on a specific use case of chatbots. How can you enhance it in giving you better results, like widening your data sets if it's on the cloud? How can you provide shorten, faster answers with the data set getting bigger and bigger? How can you enhance your chatbot using RAG specifically?
Let me show you the main figure here. Yeah. So I'm also thinking about a scenario, as you mentioned, supposing Google is running Gemini all the time and people's query come again and again. How to accommodate this RAG module to this overall pipeline? So when this large model is running, when there is a knowledge intensive query, we expect it to hand it over to the specialists, and there could be a pause in the large language model, and the specialist will generate the drafts. And when we do the evaluation, actually that's quite quick. It's like use a decoder as an encoder, so the scores will be produced very fastly. So this way, it's like when we're chatting, and then you can you hand it over to the drafter, and you can come back. And another trick we are doing here is that when we're calculating the score, we are actually caching the previous tokens in the prompt. So we are not losing the Kiwi cache for your chat history if we properly design scoring system, a scoring part. You can check it from the equations in the paper. That could be a better place to check the details. So basically, we are not changing the order of your question and the answer. So yeah, in that way, you will not lose your latency in the chatting bot scenario. I believe for the chatbot, the key difference is that you have long history and you all still want to continue the generation later. So that's what we did in this system.
amazing.
Okay, thank you very much. Thanks.
Awesome. I'll come in with a quick question as well, but obviously anyone else feel free to raise their hand if they've got another question at all. A quick question on my side. So did you do any ablations looking at how the performance changed with a number of specialists? And do you think the performance would continue to improve if you get more than 5 specialists? I would have assumed it would, because I would guess that the main benefit of this approach, or one of the main benefits, is that you get to do a large sampling across all different combinations of the documents being paired together, right? Because if you have a particular question, it might be the case that document, if you have 20 documents, it might be the case that you need document 3, 5, and 7, or whatever. And like one of the LLM, one of the specialists gets those 3, and that's the perfect combination. You get the perfect answer. But it might be the case that with 5 specialists, you don't actually get that combination of documents, and you end up with an answer that doesn't quite hit the nail on the head with the question. Yeah, anyway, so did you do any experiments with changing the number of specialists and seeing how that affects performance at all?
Let me pull out the paper directly. Yeah, this is
Amazing.
this is the ablation study we did in the paper. You can check these figures. Is this figure 3A here. We include 5, 10, 15, 20 drafts. You can consider it as 20 drafters.
So
and
like that's how many specialists you have, basically, right?
Yeah, exactly.
I guess because you had these GPU limits, you didn't do them all in parallel, but you did some of these serially, I guess. Because you said you like maxed yeah. But obviously, the number of drafters, if you technically have unlimited resources, the number of drafters would be uncorrelated with the runtime if you have enough parallelization, right? So
yeah, exactly. So the key here is that the parallelism is the key for the speed. Yeah. You can see the performance is continuing to increase.
Wow. I'm surprised you didn't try 25 and 30 on the pub health. You've not plateaued at all yet. Although hang on, pub health doc subset size. So what's going on this rightmost graph? The performance is becoming worse as more and more docs are given to each of some of the specialists.
Yeah, so we attribute this to the limited capability of your small model.
And that they just start ignoring parts of the docs if it's not like, because in a way, like if you, sorry, go ahead.
Our assumption is that if you input many documents to a drafter, to a specialist, then the correlation between the documents and the reasoning could be very complex. The model need to locate the relevant relevant doc, and it's a kind of a very big problem for smaller model. Another thing that if you input like 10 documents to the drafter, then the context will be long, and we all know when context is long, the reasoning is worse.
Makes sense. I'd definitely be interested to see what happens at 25 and 30 on the number of drafts. It seems like you should have kept going. It gets better. I wonder where it plateaus. What's your expectation on where it starts to drop off?
Yeah, that's quite interesting. We can include it in the future version.
I'll keep my eyes on the archive paper.
But the problem is that I'm not interning at Google now, so maybe I'm not sure whether it will continue my work.
There's always like tight deadlines to get things submitted in time for conferences and stuff, so there's always things you don't quite get over the line. But it looks promising. I mean, it's certainly not plateaued yet, so it looks like at least, I would expect that 25 and 30 would push it even further, it looks like. So yeah, very interesting. It'll hit a limit. Another ablation that would be interesting, I'm just thinking out loud here, but it would be interesting to ablate how much this comes down from the randomness of the model versus the randomness of the document sampling. Like, if you had 20 drafts and you kept the documents the same, for example, and you just like used the different seeds of the model, does that give you some benefit? If you fix the seed, like let's say you fix the seed and you fix the temperature and stuff, and you just give the different models, like I assume that the vast majority of the performance improvement is coming from the randomness of the documents provided to the models, but there might be some that just comes from like the sampling of the model itself, and like maybe decoupling those mutual benefits would be quite interesting. What's your thoughts on that? I guess again, it's mainly coming from the documents themselves that are being tested with the specialists. You think that's the main reason for the benefits, right?
Yeah, agreed. Because when we're sampling the document for each drop, for each specialist, there's randomness, right? We can in our experiment, we actually control the randomness with some seed. We just pick a number. But it's also worth to try different seeds and see the performance difference. One thing here is that the reason why we choose 20 as the biggest number here is because we only have 10 documents. So when I did experiment, I just think, okay, 20 should be large enough.
I got it. Okay, got it. Well, that's also because you have 2, right? The optimum selection is 2, So if you have 20 drafts, yeah, I see what you mean. But even so, the number of ways of pairing 10 documents is a lot more than 20 still.
Yeah.
It's whatever that
10 to
is. Yeah, exactly. So
45.
yeah. So yeah, it looks like it would keep improving. Yeah. I mean, I guess in a way, like the optimum way, this becomes very computation efficient, but to do the full, like ignoring the clustering, doing every possible combination of document given the subset size would obviously give you like the full search space. But I mean, for big numbers, that becomes like, you know, a combinatorial explosion. But yeah. So I guess the clustering is needed. Anyway, yeah, well, that's my questions. Really interesting. Kate Stevens has one more. Oh, there's one from Nikolai. Let's quickly do the one from Nikolai first.
Okay.
Hey everyone. Thanks for hosting this, Daniel. Thanks for the great presentation, Zilong, and interesting paper. So I have a couple of questions. The first one is just to check my understanding here. It's a very basic one. So as far as I understand, the drafter is one and the same model and just scaling it up into multiple instances. Is that correct?
Yeah, they are the same.
Okay, and then for I didn't get how the final evaluation works and how the re-ranking of the results of the drafters actually work. If you can go back to it. Sorry if that's already kind of covered. Thanks.
Yeah, I guess this is a slide for your question. Let me just give you more details on these scoring functions. So when we calculate these scores, we combine the question, the draft, and the rationale like a long string. We feed it to the large language model. We know currently our models are decoder-only models, so it is used to decode the following tokens. However, here we only decode one future token. So with this strategy, we can actually produce the probability of the next token for each token in this long string. So supposing we have 10 tokens, we generate for one step, then we will have the probability of the next token probability for all these 10 tokens we input. That's how the decoder works. So with this next token generation, next token generation probability, that's a long phrase. Yeah, for these probabilities, we average them based on this equation. So each probability is the probability to generate the next token based on the previous string, the prefix. So we just multiply or summarize the log probabilities together and do the averaging here to calculate this conditional probability. Actually, this kind of equation is similar to the perplexity, but we have some condition here. So basically, we just use this language modeling target to measure this probability as a score. Let me see if I have the more detailed equations in the paper, which may help you understand. Yeah. So here you can see we input this very long string to alpha, beta, R, and yes together to the generalist large model. And as I mentioned, we decode it for one step. So each log probability shows the next token generation probability based on the prefix. So we just multiply it because it's probability, and do some averaging and come up with the self-consistent score and self-reflection score.
Awesome, thank you.
Quick. Oh, actually, no, sorry. I was going to say a quick question, but actually, Anas has a question. Yeah, go ahead, Anas.
Yeah, you're hearing me? Is it good?
Yes.
Okay.
Yeah,
So the question was about the the probability calculation, is it in the embedded model? Like we're seeking on the cosine similarity or something like that?
I'm sorry, can you repeat the question? I not
Yeah.
that.
Yeah, the question was about this probability calculation. Is it in the
Okay.
embedded model section? Because I know that there is a principle of the cosine similarity calculation. Is it the same? Like we're calculating the score, and the score like given the semantic of the sentence or the document if they are matched or no?
It's not the same, I have to say. Here we just want to measure the two. Let me show the slide again. We want to calculate these two conditional probabilities, and we are leveraging the language models because language model is doing the next token generation. The next token is generated based on the prefix. That's a conditional probability. We leverage this thing to calculate these two probability. And as you mentioned, in the embedding systems, there's also some conditional probabilities. I think we share the similar idea because we both are using language models. Each token's generation probabilities can be leveraged in different ways. So yeah, I think if you check the code, they should be similar, but maybe we are using it in different ways. We may summarize different parts of the probability, doing some different conditions and for different usages.
Okay,
yeah.
Thank you.
Makes sense. So this first one, this self consistency is more just like an analytical thing that you infer from the logic basically, and then this other one is actually a question that you ask from the model basically.
Yeah.
Basically, yeah, it makes sense. I've forgotten what my question was now. I had one, but I've totally forgot. I guess it wasn't that important. I know we've gone over a bit. One more from Cato, which is just a very speculative one, well, high-level one, was just about kind of whether you think this is relevant for multimodal stuff with kind of maybe RAG based on images and audio, and if you have any thoughts about that.
I think, yes. Well, if you see this method in like a more overview, you can see it's actually to distribute your computation to the smaller model and you duplicate the smaller models. So one possible direction with the multi-model is that you can design several specialists for your image, for your video, for your voice, for anything. When large model cannot solve it, distribute it in parallel. It doesn't hurt the latency, and distill your job and the specialist. Then it doesn't hurt the effectiveness, and find a way to summarize them. Actually, in our current framework, we only use the large model to do the ranking and select the best one. In other way, you can use it as like a summarizer. A lot of drafts, you have a lot of drafts, a lot of drafts already. You just can summarize them to your final answer. And I think that's more feasible for the multimodal ones because I expect in the multimodal setting, maybe most of the input should be useful.
Makes sense. That actually ties to what my question was going to be, which is exactly that, which is, do you think you could push the performance more by having one of these powerful models taking all of these summaries together and like aggregating them or finding the best information across all of them and stuff? But I do think there's something quite elegant about reserving the most powerful models to just be a critic, though. And it's quite impressive that you're able to get such competitive performance where the generation itself actually has come from a smaller model, and you're just kind of like using, but also models are much better at, in general, same with people, models are much better at discriminative tasks than generative ones in general. And I think kind of, if you have very good critiquing, then you end up getting very good performance. Anyway, I could yeah, brainstorm and discuss all day, but I'll let you go. I'm sure you got a busy day ahead of you in the Bay Area, Zilong. But let's all give another big round of applause again for an amazing talk. Really, really insightful. I know you've got papers coming out all the time. A lot of, I think, mistaken hands there as we're trying to do applauses. But yeah, I know you got lots of papers coming out, so I'd love to have you again at some point. But yeah, it was a really, really pleasure to have you today, Zilong.
Thank you, Daniel, for inviting me. It's really excited to meet with everyone from all over the world. It's really happy from us. Thank you so much.
Of course, it was a real pleasure to have you. You're very welcome, and yeah, have a great week, everybody, and see you guys all again same time next week. Thanks a lot. All. Bye bye.
Have a good evening.